This video is going to cover section 4.2, the method of elimination. It's going to be very similar to what we discussed in section 4.1 in that we're going to be taking a system of DEs and using a substitution or elimination method in order to reduce the system to a single higher order differential equation, and then we'll use our methods of chapter 3 to solve. So let's just jump right on in here with example 2. You'll notice that we have a system of two first order differential equations, both of which involve the variables x and y. And so again, our goal is to solve for one variable and then plug it into the other DE to eliminate said variable and then solve that new higher order differential equation. So to begin, just pick which differential equation you want to work with. It doesn't matter either way. So I'm just going to arbitrarily choose to look at this first differential equation, and I'm going to solve for the one variable in there that is alone. So in particular, in this one, it's going to be y. So I'm going to say 2y equals x minus x prime. And so y is going to equal 1/2 x minus 1/2 x prime. Now, when I look over at the second differential equation, it gives me a relationship between x, which is what I want to work with, y, which is what I just solved, but also y prime. So in order to find an expression for y prime, I'm just going to take this expression for y and differentiate it. So y prime equals 1/2 x prime minus 1/2 x double prime. All right, so now I'm going to take the two expressions for y and y prime and plug it into that highlighted green equation. So on the left, I have 1/2 x prime minus 1/2 x double prime equals 2x minus, and let's go ahead and stick that 3 in there, 2x minus 3 times 1/2 x minus 1/2 x prime. And so that's 2x minus 3/2 x plus 3/2 x prime. And then finally, if I combine, I get a 1/2 x plus 3/2 x prime. All right, let me go ahead and multiply both sides by 2, just so that I'm not messing with these fractions anymore. So that gives me an x prime minus an x double prime equals x plus 3x prime. And then finally, if I move everything to one side, what I get is x double prime plus 2x prime plus x equals 0. So at this point, I have successfully transformed this from a system of two DEs in x and y to a single second order DE in x. And then this is just looking back to sections 3.2 or 3.3. We can solve this by setting up the characteristic equation, which is r squared plus 2r plus 1 equals 0. This factors to r plus 1 squared. And so the roots of our characteristic equation are -1 with multiplicity 2. All right, so now I can set up my solution. X of t equals C1 plus C2x e to the negative x. Whoops. And let's actually use the correct variable. These x's should be t's here. There we go. X is our dependent variable, t is our independent variable. All right, now this is only part of your solution, because if you recall, we had a system of DEs, so our solution should be comprised of two functions, x of t and y of t. So this is half of our solutions. To recover y of t, we're going to go back up here to this expression which related y with x and its derivative. So all we need to do is calculate the derivative of x of t and then plug it into that expression there that I just highlighted in yellow. So x prime of t, using the chain rule, is going to be c2 e to the negative t minus c1 plus c2 t e to the negative t. All right, so there's my derivative. Hopefully I didn't make any mistakes in that calculation. And now using that yellow expression, I want 1/2 x minus 1/2 x prime. So that is 1/2 of C1 plus C2t e to the negative t, and then minus 1/2 C2 e to the negative t. And I'm going to go ahead and just distribute this, so I have a C1 e to the negative t minus C2t e to the negative t. And let's just see if we're going to get anything to cancel here. We'll write it all out. 1/2 C1 e to the negative t plus 1/2 C2 t e to the negative t minus 1/2 C2 e to the negative t plus 1/2 C1 e to the negative t, and then plus 1/2 C2 t e to the negative t. All right, so let's take a look at what we have. We have these two terms, which we'll add. We also have these two terms, which we'll add. And then that final term is just kind of by itself. So it looks like our final answer is going to be a C1 e to the negative t plus C2t e to the negative t minus a 1/2 C2 e to the negative t. All right. So this is our y of t function. And together, y of t with x of t forms the solution for this system of DEs. So you'll notice that in this particular example, when we reduced it to the single differential equation, which would have been right here where I starred, that was a homogeneous second order differential equation. So like I mentioned, we were just referring back to our knowledge of sections 3.2 and 3.3 to solve for that. It's possible that your examples also have some external function, in which case you would have a non-homogeneous DE. And so that leads us to our next example here on page 5 of the notes, problem 8. All right, so the difference here is this external function showing up in the y prime function. So just because that external function is there, I think what I'll do is I'll choose to work with this first differential equation because it's simpler in some sense. So I can write y as x prime minus 2x. And then again, the goal is to plug everything into the other differential equation. So we just need to also have y prime. So y prime would be x double prime minus 2x prime. So now I'm going to plug the expression for y and y prime into this second differential equation, which I've just highlighted. So plugging into there, we have x double prime minus 2x prime equals x plus 2x prime minus 4x, and then minus r e to the 2t. So what I'm going to do is I'm going to take these three terms here and move them over to the left-hand side. So that's going to give me x double prime minus 4x prime, and that's a negative 3, so it'll become a positive 3x, and this equals negative e to the 2t. So at this point right here, we're back into the world of section 3.5, where we have a linear non-homogeneous DE with constant coefficients. And so we need to go through the steps of finding both the complementary function and the particular solution while being sure to check whether we have any duplication. So let's start by setting up the characteristic equation for the associated homogeneous DE. That's going to be r squared minus 4r plus 3 equals 0. That's going to factor to r minus 3, r minus 1. And so our roots are real and distinct numbers 1 and 3. So we can set up our complementary function is going to be C1 e to the t plus C2 e to the 3t. All right, so now what I want to do is I want to look at my external function f of t, which is e to the 2t. Technically, there's a negative there. And I'm only getting one term from this function, namely e to the 2t. Because if I keep taking its derivative, I'm going to keep getting the same functions back out, e to the 2t, with different weights in front. So I conclude that I do not have duplication. So for my guess at my particular function, I just have sum a e to the 2t. So this is a rather friendly problem because that's going to be an easy function to solve for its coefficients. If I go back and look at my non-homogeneous DE, which I just highlighted, I need the first and second derivatives. So let me just list those here. The first derivative is 2a e to the 2t. The second derivative is 4a e to the 2t. So now I'm just going to plug those three functions back into the original non-homogeneous DE. 4a e to the 2t minus 8a e to the 2t plus 3a e to the 2t. And all of this has to equal a negative e to the 2t. So if I combine these together, I have 4 minus 8 plus 3 is a negative a e to the 2t equals a negative e to the 2t. Whoops, sorry, not negative. That's positive up there. All right, so we get right away that a equals 1. And so we now conclude that our particular function is just e to the 2t. So now the general solution for the x of t, remember we want to take our complementary plus our particular, is going to be C1 e to the t plus C2 e to the 3t plus e to the 2t. So here's our x of t function. Let's box that in. That function comprises half of the solution to our system of DEs. And now we'd like to find y. So again, coming back up here, I'll highlight in a different color. Looking back up at our expression for y, we know how y relates to x in its first derivative. So let me just copy that expression down below. Y equals x prime minus 2x. Okay, make sure I got, nope, should be minus. Wanted to double check. And so let me plug in that derivative. First of all, that's going to be a C1 e to the t plus a 3C2 e to the 3t plus a 2 e to the 2t. And then I want to subtract off 2 times the original function, which is C1 e to the t plus C2 e to the 3t plus e to the 2t. And then let me just cancel where I can or simplify. Looks like I have a positive 2 e to the 2t and a negative if I distribute this 2 everywhere. And then I can just combine the remaining terms. So it looks like my y of t is going to be a negative C1 e to the t, and then a 3 minus 2, so a positive C2 e to the 3t. And so here is our y of t function, and again, together x of t and y of t form a solution for this system of DEs. So we have now seen an example of when you might have a non-homogeneous DE once you simplify. We have one more example in this section, And it's just going to be illustrating how we can use this method with higher order systems of DEs. So let's just take a look here at number 12. We want to find the general solution of this system. And again, the only difference here is that we're seeing second derivatives instead of just first. So this is a system of second order differential equations. But thankfully, we don't have any external f of t functions. So this should reduce to a homogeneous DE of higher order. Since we're starting with second order DEs, it's likely going to turn into a fourth order DE. So as always, just choose which function you want to work with or which equation you want to work with. I'm going to work with the first one. So this is 2y equals x double prime minus 6x. And then if I solve explicitly for y equals 1/2 x double prime minus 3x. So here's my expression for y. When I look at this second DE, I do need an expression for y, but I also need an expression for the second derivative. So I'm not even going to worry about the first derivative, but the second derivative, y double prime, is going to be 1/2 the fourth derivative of x minus 3x double prime. All right, so now let's plug these two expressions into that yellow equation. So I have 1/2 x fourth derivative minus 3x double prime equals 3x plus 7 times y. So 7/2 x double prime minus 21x. All right, so the first thing I'm going to do is multiply by 2, just so that I don't have to monkey with those fractions. Fourth derivative of x minus 6x double prime equals 6x plus 7x double prime minus 42x. And then finally move everything to the left-hand side. So that's going to give me the fourth derivative of x minus 13x double prime. And let's see, what's 42 minus 6? 36. So plus 36x equals 0. All right, so we're back into the happy world of section 3.3. My characteristic equation for this homogeneous DE is r to the fourth minus 13r plus 36. And I believe this factors r squared minus 9, r squared minus 4. The authors were nice to us because this factors nicely. So this, for my roots, I get plus minus 3 and plus minus 2. So I have 4 distinct real roots. I can then set up my solution. Notice I'm not writing the subscript C for complementary, just because this is homogeneous. So there is no complementary versus particular, there's just the solution. So I get C1 e to the 2t plus C2 e to the negative 2t plus C3 e to the 3t plus C4 e to the negative 3t. All right, so here's my setup for x of t. I'll go ahead and box that in as half of my answer. Okay, and now we would like to find y. So as always, just going back up and looking at the expression that I had that related y to x and its derivatives. I'll just recopy that down here, 1/2 of x double prime minus 3x. All right, and I feel fairly confident that I can find x double prime without writing the first derivative. So here it goes. If I take the derivative twice, it's going to pop out 2 2's, so I get a 4 C1 e to the 2t. Similarly, it'll pop out 2 negative 2's, which will make it plus 4 C2 e to the negative 2t. Then I'll get a plus 9 C3 e to the 3t plus 9 C4 e to the negative 3t. Okay, that comprises my second derivative. And then I have minus, I'm going to just distribute this 3 everywhere, 3c1 e to the 2t minus 3c2 e to the negative 2t minus 3c3 e to the 3t minus 3c4 e to the negative 3t. And then from here, all you want to do is collect like terms. So for the c1 e to the 2t's, remember to distribute your 1/2. So I have a positive 2 and a negative 3, which is going to add to a negative 1. And then we'll just go pairwise again. We have a positive 2c2 and a negative 3c2, which is going to give me also a negative c2 e to the negative 2t. So moving on to the e to the 3t's, I have 9/2 minus 3. So that's 9/2 minus 6/2 for a total of 3/2. C3 e to the 3t. And then finally, same for the e to the negative 3t's. All right, and we'll box that guy in. And there we have it. Our solution to this system of second order differential equations is given by x of t and y of t as shown.